So hello everyone, my name is Luca Nella and I work at Power Lab here at EPFL. Today I'd like to give you a short overview on our current project, which is called Gallium Nitride Integrated Circuits for more efficient and compact power conversion. So first of all, what is power electronics? So power electronics takes care of the transformation of energy all the way from its generation to its final consumption. And there are many domains that you can be familiar with, for instance, traction, such as electric vehicle or train or any home appliances or any electronic device that you're currently using. What you see, however, is that as you go from the generation all the way to the consumption, a large energy amount of energy is actually lost, about 10 to 20%, which results in actually huge energy losses, which means that even a small increase in the efficiency of such process can actually be huge and very beneficial. So now to give you, and for instance, what we focus more on is more this part, so the one closer to the energy consumption sides. And to give you like an idea of where you can encounter power electronics in your everyday life, every time that you use your laptop, you know that you have to plug it in order to recharge it. But what you may not know is that not all of the energy that you draw from the line actually goes to your computer because there are significant losses. And this you can easily verify by considering that the transformer that you plug in usually gets hot. On the other side, you can usually you want to buy a super lightweight computer so that you can carry it around quite easily. However, this usually comes with a big transformer box, and which is required in order to recharge it. And of course, reducing this size could be highly beneficial, but while for you it can be just a bit more convenient solution, actually there are some applications such as aerospace where every kilo matters. So by reducing the size and space that the power conversion system takes, you're actually also making it much more efficient. So in order to tackle these two problems, what are the main approaches? First of all, we need to reduce these losses. And this can be done, for instance, by using a more suitable semiconductor material with respect to silicon, which we are all used to, but especially also using a better device design that is really fundamental. On the other side, we want to reduce the size of our device. And we have a very clear example how to do that. If you consider any computer, you have billion of transistors packed in an extremely small size. And this is made possible by the fact that you can integrate many of these on the same substrate, like they do in CMOS logic. So now let's see how we can actually tackle these two issues. So first of all, what about the material? So what we use is called gallium nitride. This is a nitride material, which is mostly known at the moment for LED lighting. All the LED around are made of GaN. But it has an excellent material performance also for what concerns power. And here you can see just a quick overview. On the other side, and a very important point of gallium nitride is that it has a lateral architecture. So you can have source and drain on the same side. So which means that the current just flows horizontally and comes out from this. This is basically the same that you have for silicon logic, which means that you can easily integrate many devices on the same chip and realize ICs. So now let's see, once we chose the material, how to design a device based on that. So what we propose is a nanostructures for power devices, which can be a bit counterintuitive because as you consider a power device, you typically think of a big chunk of semiconductors. But actually what we can show is that by nanostructuring such devices in a very similar fashion to what happens for FinFET, you can actually improve significantly the performance. And here you can see a zoom-in real device all the way from its multi-finger structure, which is used to scale up the current, to its single finger structure. This is a typical diode where you have a cathode and an anode and a long drift region in order to hold the voltage. And we see that here we can nanostructure the anode into nanowires, which are about 200 nanometer wide, and this significantly improves the performance of such device. Here you can see, I won't go too much in details, but you can see that you can enhance their own performance, so basically have a faster diode turn on with a higher current, while at the same time reducing the leakage current, which means that you can hold more and more voltage, which is mainly the point of a power device. And overall, what you see is that you can achieve an improved figure of merit with respect to commercial state-of-the-art silicon and silicon carbide devices. So this GaN nanostructuring really is very useful in order to take full advantage of the properties of this excellent material. On the other side, what about the integration? So we saw that we have a lateral architecture, so now we can try to integrate many devices on the same substrate. And here you can see that we integrated 4 power diodes, all on the same substrate, in order to realize a DC to DC step-up converter. This is, for instance, a very useful circuit for a photovoltaic application. And what we see is that the active part of the circuit is all in this very small integrated circuit, which contains up to 4 diodes, and it's just a few millimeter by few millimeter. So now we compare this to what we can do actually in the state of the art. And it's clear that you can achieve an ultra compact design with respect to what is commercially available. Here we see we have 6 silicon and silicon carbide devices, and we can achieve the same functionalities, the same ratings in a much smaller, few millimeter by few millimeter GaN IC. On the other side, we can see that we can also keep a high efficient operation, and especially we can even operate at much higher frequency with respect to silicon, which is highly beneficial because it allows to further reduce also the passive component size. So overall, we saw that this kind of GaN nanostructured devices are extremely promising for IC, which lead to compact and high efficiency converter. So as a conclusion, what we quickly saw today is that GaN is an excellent material for power conversion due to its intrinsic properties. However, then we need to take care of how to design an optimal device made of GaN, and nanostructuring really allows to take full advantage of the material properties. Lastly, we saw that we can, thanks to the lateral architecture of GaN, we can integrate many devices on the same chip in order to realize power integrated circuits, which really allow to reduce the size of the converter in order to achieve ultra compact, but also very high efficiency converter. So thank you very much for your attention. And if you're interested in the topic, you won't have any more questions, just please drop me a message. Goodbye.